Hi, this is a recitation about dimensional analysis in chapter 1, and this is end of chapter problems in your textbook, the main textbook, Survey and Hewitt. And this shows the question number at the end of the chapter 1 that I'm working on. Okay, so let's start with question number 9. The question is, which of the following equations are dimensionally correct? And the first one is let me write it down in here. Vf stands for final velocity is equal to Vi plus A times x. So is this equation dimensionally correct? Well, we don't know whether this equation, is physically correct or not. We don't care about it, but we only analyze its dimensional correctness. What I mean by dimensional correctness is this is an equality, and what we need to be correct dimensionally is that either side of the equation, left and right, must have the same dimension. Okay, so first of all, let me write down the known dimensions of the expressions, the quantities in this equation. So Vf stands for final velocity, and its dimension is nothing but length divided by time. Okay, and Vi is again velocity. It is initial velocity. Again, it is length divided by time. And A stands for acceleration, and acceleration dimensions are length divided by time squared. And x stands for length measurement in the x direction, and its dimension is L. Okay, so what we do is we just take the square bracket of every term in this equation. Okay, square bracket means whenever you see a square bracket, just put the dimension inside the square bracket, whatever the physical quantity inside, is put the dimensions of them. So let me write down this, and square bracket A multiplied by square bracket X, because these are multiplied by each other. So this is equal to L divided by T, and so that this one specifies that the right hand side of the equation, every term in the right hand side of the equation as the sum units, must have the dimension of L divided by time. Okay, and this is L divided by T. So the first expression on the right hand side just verifies or obeys the correctness, and plus A is L over T square, and X is L. There is a multiplication over here. So the last term on the right hand side is just L square divided by T square. Okay, but L square divided by T square dimensionally is not equal to L divided by T, right? So these two expressions cannot be added. That means we don't know whether this equation is physically correct or not, but at least we are sure that dimensionally it's not correct. So that means this equation cannot even be physically correct. Okay, so next is the second term, B, second part of the question. Y is equal to 2 meters multiplied by cosine kx. Okay, this is 2 meters, this expression over here. It is a numerical expression, but for this numerical expression, we know what the unit for this expression. Let's first take the square bracket for every and each quantity over here, cosine kx. Okay, so y has, since it's y coordinate of something, then it has the unit of L, length, and since this is not a just number but it has also dimension next to it, meters, so its unit is L. And this one, cosine of something or sine of something or tangent of something, whatever, every trigonometric quantities has, every trigonometric quantity has the dimension of 1. It has no any dimension, so it's just 1. All right, So that means this equation can dimensionally be correct. Okay, so because the left hand side of the equation is in the dimension of length, and also the right hand side of this equation has the dimension of length. Okay, all right. So next, let me refresh the page. Okay, so next question, and you may pause the video and just read the question, but let me explain what the question is about. The question number 10, chapter 1, and what you see over here, it's a cone, but it's a truncated cone. It's called the frustum of a cone. All right. So cone has this top cross section, which is a circle, and the bottom cross section is again a circle. What you see over here is R1, which small r1 is nothing but the radius of this top cross section circle, and R2 is the radius of the bottom circle. And also what you see over here is h, which is the height of the cone from the bottom circle to the top circle. Okay, so the question says there are three terms over here, three expressions, sorry. These are three expressions, and these three expressions, it says one of these three expressions gives the total circumference of the cone, the top and bottom, the total circumference of the flat circular faces. And one of these three of the equations is the volume of the cone, and one of these three of the expression is the area of the curved surface. So which one is which? Obviously, what we do over here is we just analyze three of these expressions dimensionally and just find what the dimensions of three of the expressions A, B, and C. And from this dimensional analysis, we will be able to pick up one of them is circumference, one of them is volume, and one of them is area. Okay, so let's start with the first one. Let me write over here A. It is pi R1 plus, sorry, let me just don't cross, let me put over here A is pi, okay, R1 plus R2, and this is going to be multiplied by this expression in the square bracket h square, sorry, it's not h bar, it is h square plus R2 minus R1 square, and the square bracket has pardon my writing, it's not fitted over here. Let me quickly write it again. Pi R1 plus R2 h square plus R2 minus R1 square, and square bracket in parenthesis, close the parenthesis, take the square root of the square bracket. Okay, so this is the first picture. How do you find the dimension of this expression? Take the square bracket of every and each term. Well, pi is just a number. It has dimension 1. Well, this curly bracket has inside the sum of the two radii of the circles, where radii has the dimension of length, so it's just L, okay? And this is going to be multiplied by the square bracket. Well, h square is the height square, but height has the dimension of L, so it is L square. And obviously, this is added to the curly bracket square, which is R2 minus R1 square. Well, R2 minus R1 is just, again, has the unit of L, so length, and take the square of this, so it is L square again, and 1 over 2. Okay, So L square plus L square is nothing but L square, because if you add two dimensions which are the same, this is the dimension itself, okay? So this summation is just L square. Remember, we are not adding some numbers, we are adding the dimensions, okay? So when you're adding the dimensions, when you see both expressions which has the same dimension, just it's the same, it's one of them. So L square square root is nothing but L, right? And we have also L over here multiplied by L. So this expression has the unit of L square, which is nothing but area, because area, it has the unit of length square. So that means the first expression corresponds to the area of the curved surface, which is, okay, F. So A is to F. Next is, let me write it over here, B 2 pi in curly bracket R1 plus R2. That's it, right? Well, it's very obvious that dimension of 2 pi is just 1. Dimension of R1 and R2 is just L. So this has the dimension of length, which is the circumference. It is the circumference of two circles of this cone. And C, quickly, pi h multiplied by R1 squared plus R1 multiplied by R2 plus R2 squared, and this is going to be divided by 3. So the first term is pi, which has dimension of 1. The second term is h, which has dimension of L, multiplied by this curly bracket inside, as every term has the dimension of L square, so just put L square. And 3 has the unit of 1. So if you multiply L square by L, you get L cube, which is nothing but the dimension of volume, okay? Dimension of volume is nothing but the length cube, right? And C corresponds to the the volume of this conical geometrical object. Okay, so that's good. And let me also clear this page off. All right, and next question. Okay, so this is the next question. Again, chapter 1, the end of chapter problem number 12. So it says about a law, universal gravitation law, is given by this formula, which is F stands for the force between two objects. One object has the capital mass m, the other object has small mass m, and G is a physical constant, and R is the distance between these two masses, the physical distance, length distance between these two masses. So it's about the force, attraction force between two masses, okay? This is called the universal law of gravitation. And what it says over here, F is the magnitude of gravitational force, and these small m, capital M's are masses. So it gives these what these are, because we will be able to write down what the dimensions of these quantities, right? And R is a distance. It says force has the SI unit system, in the SI unit system, kilogram meter per second square. So what are the SI units for the proportionality constant, or the physical constant G, capital G? Let me write down in a larger way this expression R square. Okay, so again, it's a dimensional analysis problem. So this I will take a square bracket of every term, and that means square bracket of F. So what the question is about is just what is this square bracket G, all right? This is the question. What is the dimension of G, the physical constant, universal gravitational constant? This is called universal gravitational constant, okay? And this is the question. So this is capital G square bracket, capital M square bracket, small m square bracket divided by small r square bracket square. You can take the square outside the square bracket. So this must be equal to, since this is given, kilogram meter per second square, okay? And I will just put, instead of r square, where r is the distance, so it has the unit of meter, and it is meter square, right? Over here, meter square. By the way, this m and this m are not the same thing, okay? This m refers to a small mass, and this m refers to the length measurement in SI unit system, which is meter, all right? So then this m, square bracket of this m, is nothing but kilogram. And similarly, the square bracket of larger mass is again the same unit, kilogram. So instead of 2 kilograms, I can write down just kilogram square, right? And this is unknown. So if I just solve for this, what we have is, after some simplification, this kilogram may just simplify one of the kilogram on the left hand side, and we have meter square, meter over here. We will have meter cube on top, and we will have kilogram second square on the bottom. So this is the dimension of the gravitational constant in SI unit system. Well, if you want to write down the unit for the gravitational constant for every unit system, you will write, since this stands for meter, L cube, and this is M, and this is T square. So this is the universal unit for the universal gravitational constant, okay? For example, if you want to express this universal gravitational constant in units of, let's say, CGS unit system, then you will put that just instead of L, centimeter cube, and M is gram, and T is second square. Okay, I hope this is clear for you. So let's clear this out. Do we have a next question? Let me see. Yes, I think this is the final question for today. All right. So question number 14, chapter 1. We have again an equation which is x is equal to a t cube plus b times t. These a and b's are some constants. It says the described motion of a particular object with x having the dimension of length and t is having the dimension of time. Determine the dimensions of constants a and b. So let's do the first part of the question. So we have this expression, equation a is equal to a t cube and plus b times t. Again, a dimensional analysis problem. If you take the square bracket for every term, assuming that this expression is correct, we have L over here, so that means this must have the unit of L and this must have the unit of, again, L, because we have a sum over here. And if a t cube, if you want to write down this like t cube is equal to L, and we know that dimension of small t is nothing but capital T, right? So that solves the dimension for A to be L, length divided by time cubed. And next is dimension of B, T. This is B, dimension of B, multiplied by dimension of small t, and this is going to be equal to L. Again, dimension of B multiplied by time is equal to L. That means dimension of B is going to be equal to just length divided by time. So we just solve the dimension of A to be length divided by time cube, and dimension of B to be length divided by time. And next part of the question says that determine the dimensions of the derivative dx over dt. So dx over dt, I assume that you know what dx over dt is. Just the derivative of this x function with respect to time. Okay, dx over dt. Well, let's do this. I mean, well, it's already done. I mean, the expression is given 3 times a t square plus b. Okay. So what is the dimension of dx over dt? Well, you can treat dx over dt as the division of dx, whatever it is, by dt. Again, whatever it is. But we know what dx is. What is dx? Dx is small length in the x direction. Well, after all, it's length, right? It has the dimension of L. Again, dt is incrementally, infinitesimally small time value, just like dx. Dx is infinitesimally small length value, and dt is nothing but time. So that makes this equation unit is L divided by t. Let's check it. Well, 3 has no dimension because it's just a number. Well, A has the dimension L divided by t cube, and this is going to be multiplied by small t square, but small t square has the dimension of t square. Well, is that L over t? Yes, it is. Really it is indeed. And t square divided by t cube is just 1 over t, so it makes this L over t. And B has the dimension of L over t, so everything is verified. All right. So that's it. It's all about dimensional analysis problems. And this will complete today's mini lecture.